Today topic is dipole moment. Dipole moment. Dipole moment is in different ways you can explain. I think first based on the molecule in AB molecule, ionic character. In AB molecule, ionic character is proportional to Xa minus Xb. So ionic character depends on, means Xa is what here? Electronegativity. So ionic character depends on difference in between electronegativity of two elements. Okay, see. All right, look it up. Yeah. Now here Xa and Xb are that only. What Xa and Xb are electronegativities of A and B. Now ionic character is calculated as (16) into Xa minus Xb plus 3.5 into Xa minus Xb square. This is one formula. If ionic character is equal to 0, okay, equal to 0, when it is happen, Xa minus Xb or Xa equal to Xb. Xa minus Xb equal to 0 or Xa equal to Xb. That is 100% covalent bond. Okay. That is ionic character equal to percentage of ionic character equal to 0 minus 15, suppose, means one is 15, another one is 0, then it is what now? In 0 to 15. Ionic character equal to what here? 0 to 15%. Then it is non-polar covalent bond. Means not only equal to 0, okay, ionic character is 0 to 15%, then that is what here? Non-polar covalent bond. Non-polar, example C, H and H is there. Actually, electronegativity of hydrogen and hydrogen are equal. So electron difference is equal to 0 in this case. H and H. Okay, both are same elements. So then ionic character 0 you can write. But that case you can apply till 15, means electronegativity of two elements till the 15%, then you can apply, not only 0. Not okay, restrict to 0. Next is percentage of ionic character, percentage of ionic character equal to 15 to 50%. Suppose. Then you can tell this is the polar covalent bond. Okay, 15 to 50%. Then what you can tell, that is the polar covalent bond. That is polar covalent bond. Okay. Suppose percentage of ionic character. Percentage of ionic character greater than 50%. Okay. Then ionic bond. You can tell that is the ionic bond. Now you can take the polar covalent bond extension. In polar covalent bond only you will get the dipole moment concept. So polar covalent bond. If you take the polar covalent bond, in this case, okay, electron difference between two elements is not equal to 0. That is between 15 to 50%. What you can define, if a covalent bond, covalent bond means sharing of electrons, is formed between, okay, two different electronegativities having most non-metals, that is, okay, percentage of ionic character equal to from where to where, 15 to 50%. Okay, then the covalent bond is known as what here? Polar covalent bond. Sound తగ్గించిన sound తగ్గిస్తా. Polar covalent bond. Okay, electronic difference is there, but percentage of ionic character is 15 to 50%. That also you can write electronic difference base also you can tell bonds. Okay, 1.7 is electronic difference. Then that is ionic bond. Electronic difference is 1.7, that is ionic bond. Electronegativity difference, okay, greater than 1.7, that is less than 1.7. Electronic difference less than 1.7, that is comes as covalent bond. In that again, polar covalent, non-polar covalent. Here electronic difference greater than 1.7, that comes as what here? Ionic bond. Right? So we can observe both ways. Now we are observing the covalent bonds, that too again polar covalent bonds. Polar covalent bonds is always found between two different electronegativities having elements that should be again more than 15 to 50% ionic character. Now this type of polar covalent bond having compound I am taking, that is example HCl. HCl, chlorine have some electronegativity, hydrogen have electronegativity. So electron difference, observe, that is greater than, okay, ionic character related 1 point, okay, 15 to 50% will come this. In this case, chlorine will show the negative charge, hydrogen positive, means partially negative, partially positive. Why means, according to covalent bond, sharing of electrons between two atoms. That is only no. Covalent bond means what? Sharing of electrons between two atoms. But here, if you observe the hydrogen have the nucleus, it have one proton only. Chlorine have nucleus, it have the 17 protons. Sharing hydrogen, it is 1s1, it is what? 1s2, 2s2, 2p6, 3s2, 3p5. Okay, chlorine atomic number base. So that 3p5 last electron is in the bonding now. Okay, now chlorine 17 protons attracting these electrons, and hydrogen one proton attracting. Both are attracting the paired electrons, but it has more nucleus charge than this one. That's why the electrons will be moved towards the chlorine side after forming bonding. Not complete transfer. Complete transfer means you will write Cl minus H plus. In this case, not happened. Actually, what is the distance from the nucleus to the 1s1 electron? That will be expand. Okay, so that will goes to that side, and the chlorine attract these electrons. So now this hydrogen loss some of the negative charge. So partially positive will write. Chlorine will gain some of the extra negative charge. So partially negative. So this is known as what here now? Charge. Okay. Partially charges are developed. Now here the distance between two dipoles. Okay. These two dipoles you can take D. Then the product of magnitude of negative or positive charge Q and distance D between the centers of positive and negative charges is called dipole moment. Okay, what is the dipole moment? It is the product of the magnitude of the negative charge or positive charge and the distance between the centers of positive and negative charge is called dipole moment. Dipole moment is denoted by nu here. Okay, dipole moment is denoted by what here? Nu here. So nu equal to, okay, you can write the nu equal to delta into DRL. Okay, nu equal to delta into DRL. Otherwise, delta you can write charge Q and D is the distance between two nuclei. Now, the charge Q is of the order of the charge Q is of the order of what is the charge value you can take. Actually, the charge will be taken in the values of electrostatic units or coulombs. So charge in the order of 10 power minus 10 electrostatic units, and the intermolecular distance, you can tell this is intermolecular distance. Intermolecular distance or internuclear distance. What is the 10 power minus 8 centimeter? Okay, is 1 angstrom. Internuclear distance is 10 power minus 8 centimeters or 1 angstrom. Therefore, the dipole moment, how can you write? Suppose means this is the 1 unit charge. 1 unit charge is 10 power minus 10 ESUs, and the distance between the two dipoles means here HCl is there, Cl minus H plus. Distance between two nuclei is 1 angstrom. Then dipole moment nu equal to what you can write? 10 power minus 10 into 10 power minus 8. You can write that one now. So this what you can write 10 power minus 18 ESU. So this quantity is what that value 10 power minus 8. You can write 1 dB. Right? This is a 1 dB. So one information you want to get. Dipole means it has the magnitude and as well as direction. It has the magnitude as well as much of the dipole distance. Distance, this charge will move this side. So it will have direction and some magnitude. Now it is often represented as by arrow. That means according to vectors, which is shown by arrow. You know that positive charge side should be the tail, negative charge side should be the head. The representation is plus towards arrow might be from observable information. That means which side. Next is diatomic molecules. Diatomic molecules, as per diatomic molecules, possess only what here? One polar bond. Okay, diatomic molecules have taken only one polar bond will be there, right? And also molecule is equal to the dipole moment of the polar bond. Let's see, diatomic molecule example you can consider HCl here. Diatomic molecule have only one polar bond. Okay. If you are taking tetraatomic, then it will have different bonds, so that polar bonds you can consider. But diatomic molecule only have the one polar bond. So that is example HCl. It is negative, it is positive, already defined. According to calculated, multiplied, and substitution, the dipole moment of HCl is 1.03. Next is the case of some polyatomic molecules. We are going to see here polyatomic molecules. Polyatomic molecules have taken, that is, as polyatomic molecules have more than one polar bond. Okay, and dipole moment is equal to the resultant all individual bonds. Resultant dipole moment of all individual dipoles individual bonds. Okay, dipole moment of all individual bonds. For example, you have considered, suppose H2O is considered. H2O is 1.84 dipole moment is having, which is equal to resultant dipole moment of two OH bonds. That is H2O structure. You see that it have this way. It have two dipoles. One is oxygen negative and hydrogen positive. Prime is oxygen more electronegative than hydrogen. Same way oxygen negative, hydrogen is positive. So this way movement. Now here two dipoles is there due to the two OH bonds. Okay, two OH bonds is there. So two dipoles will be there. So in this case, dipole moment 1.84 dB. Right, net dipole moment. Next, consider CO2 molecule. Next example. CO2 molecule. In this case, so CO bond is polar. CO bond is polar here due to the electronegativity difference. Okay, here CO bond is polar. Why means oxygen more electronegative than what carbon? So oxygen gets negative charge, carbon gets positive charge. There is the what here? Polar bond. CO bond is polar bond. But the resultant dipole moment of overall molecule. But the resultant dipole moment of CO2 molecule is zero. Okay, the resultant dipole moment is zero, as individual dipole moments are of equal magnitudes and opposite sign. As individual dipole moments, what here? Opposite and equal. So that's why in this case dipole moment of CO2 is zero. How that you consider CO2 have this type of structure? Okay, imagine then this movement is this direction, this movement is in this direction. Both are equal and opposite. It is linear molecule. So net charge on this molecule is zero. So dipole moment of this molecule is zero. Okay, understood?
Yes.
Okay. Copy this one. Okay, next is other molecules also you are going to check here. Other molecules are, suppose fourth case. Door close cheyade akkada. In case of symmetrical molecules, we have taken In case of symmetrical molecules, such as boron trifluoride, this is symmetrical molecule, CH4 and CCl4. The molecular dipole moment is found to be 0. The molecular dipole moment equal to 0. The molecular dipole moments to be 0. What is that? Suppose we have taken CH4. In this case, the bond moments C, okay, have the more electronegativity than hydrogen. So bond moment is towards carbon side. Here also carbon side. Here also carbon side. Carbon side. So I means carbon have more electronegativity than hydrogen. So net dipole moment in this case is equal to 0 here. Similar, okay, CCl4 also. CCl4 we have taken. In this case, chlorine more electronegative carbon. Now bond moments are this direction. Okay. Now these four all moments will be cancelled by each other. Then dipole moment of this molecule also 0 here. In this case, dipole moment is 0. In this case, dipole moment is 0 here. Now, applications of dipole moment. See, you got idea. First is what? Diatomic molecules. Dipole moment is some cases 0. Okay, if it is non-polar molecule, like HCl you have taken. See, like what here? HCl you have taken. In this case, okay, dipole moment is not equal to 0. Why means diatomic molecule unequal polar bonds. Unequal polar bonds. Okay, equal polar bond dipole moment 0. So that's why dipole moment is 0. Poly molecules are seeing in this case H2O diatomic molecule. Here dipole moment will be there. Why means this case, okay, net dipole moment is not equal to 0. Mahasri. Same way CO2 case. Triatomic molecule CO2. But in this case, dipole moment is what? 0. Why means here equal and opposite. But here not equal opposite. See, these are not opposite, same direction. Okay. Similar CH4 we have observed. And also CCl4 also we observed. CH4 case also net dipole moment going to 0. CCl4 case net dipole moment 0. And BF3 case also net dipole moment going to 0. Next, we are going to study about, okay, till here only have. Then applications case also you can see some information about dipole. Here, in determining polarity of bonds, what are the uses of this? Determining polarity of what here? Bonds. Bond have polarity, now polarity can determine by using this. Means we have the dipole moment formula nu equal to Q into D. In this case, greater is the magnitude of dipole moment, higher will be the polarity of bond. How this is? You have taken some compound AB. Suppose it is electronegative, it is electropositive, it gets negative, it gets positive. Here more charge is developing then here charge also more comes. Then net dipole moment D anyhow. So it is one factor. Then polarity of bond is more, then dipole moment is more. So greater the magnitude of dipole moment. Chinno. Okay, this way. Next is further in case of the non-polar molecules we have seen. Non-polar molecules, example like O2, N2, H2, these dipole moments anyhow 0. Why means you know that no polarity. Like, okay, 0 charges. So del Q is 0 in this case. Then dipole moment finally 0 will come in this case. Next is the case of calculation of ionic character. You can this case. You can use this. Second application. In the calculation of ionic character. In the calculation of ionic character also you will use this. How that means? A covalent bond develops a polar character due to the difference in the electronegativity. No polar bond. So electronegative atom forming the bond. Okay. Next is second. If the electronic difference between two atoms is large, doubly polar. It has been observed that when electronegativity difference is 1.7, the bond existing between two atoms is 50% ionic, 50% covalent. So not needs to calculate. Of ionic character 1.7, what here covalent bond. The percentage of bond can be calculated from the ratio of observed dipole moment to the calculated dipole moment. Observed dipole moment by calculated dipole moment into 100. Okay, this is the what here percentage of ionic character.